In the last unit, you've seen the concept of a for expression. What we are going to do now is use for expressions in a novel and interesting application, namely the generation of random values. So far we have seen for expressions operating on lists, on sets. In the previous course we have also seen them on databases and options. All these things are collections of data items in some sense. So the question is, are for expressions good only for collections? And interestingly, the answer is no. All that's required is some interpretation of the map, flat map, and with filter functions that make sense for the type in question. There are many domains outside collections that have such an interpretation, and an example that we are going to see now are random value generators. So what are random value generators? You know about random numbers from a language like Java. Here you would import JavaUtil_random, create a new random number generator, take the next random number off with nextInt. A question now is there a systematic way to get random values for other domains? For instance, we want random booleans, random strings, random pairs, lists, sets, or trees. So here's a way to do that. We define a trait generator with some element type t, and that would generate random values of type t. Here's the outline of that trait, so it's generator. Here's the type of values that get generated, and here's the function generate that does that. Let's look at some instances of this type. The first instance generates random integers, so that would now be packaged as follows. The integers generator is a new random generator of type int. It defers to the Java integer generator, and its generator method just picks off the next random number from rand, the Java random number generator. What about booleans? Well, once we have a generator for integers, booleans is easy. We create a new generator boolean. Its generator method just generates a random number using the integers generator and asks whether that random number is greater than 0. If it is, we return true. If not, we return false. What about pairs? Well, here's a generator that gives you pairs of integers. Its generate method calls generate twice on the integers generator and packs the results in a pair. Now all this works, but it's also a bit cumbersome. Each time we have to set up a new anonymous class of type generator, define a generate method, and so on. Question is, can we do without all that boilerplate? Ideally, what we would like to write is something like this. To get booleans, we just say for x taken from the integers generator, yield x greater than 0. Or for pairs, we would like to say that let's have two generators of two arbitrary types t and u, call them lowercase t and u. Let x be taken from t, y be taken from u, return the pair of x and y. Now if you want to do that, then a good question is, what does the compiler expand this to? Here's what it would do. Booleans would be expanded to a call to map, and pairs would be expanded to a call to flat map followed by a call to map, according to the expansions of for expressions that you have seen in the last unit. So you see that as long as we have map and flat map defined on the generator class, we can actually use the convenient syntax with for expressions. So let's see how we would define map and flat map on the generator class. Let's start with map. So here's the type of map. It takes a function from the random value type t to a new random value type s, gives you a generator of s. And the way it would do that, it would generate random numbers of type t using its own generate method, then apply f to those random numbers, and those give you the random numbers on the s type. There's a twist here in the call to self.generate. If we had written just generate, that would be, according to the expansion rules in Scala, this.generate. But the this in this new anonymous class would refer to the current method that we define here. So it would be a recursive call to the generate method, which would not terminate. What we need instead is we want to call the generate method of the object one further out. That's this generate method here. And the way we can achieve that is that we define an alias for the this value of this object out here using the syntax self arrow. So that would define an alias name for the this term of the class over here. So writing then self-generate would defer to this method over here. Another way that could be achieved in both Java and also Scala would be to prefix the this with the name of the class. So we could have written generator dot this dot generate, and that would have done the same thing. So the second thing we have to do is define flat map on generators. Here it is. Again, it's useful to compare with map. So flat map would give us back now a generator of s from the function f. So it takes a random value to a whole sequence of random values to a generator, and its result type is again generator of s. Its generate method is implemented as you see here. So what we would do is first generate a random value of type t using self.generate as before. Apply the function f to it. So that now gives us a complete generator on the new domain s. And to pick a random value in that domain, we invoke generate here again. Now that we have defined the general machinery that we needed on class generator, we can look at some specific generators again. So booleans, here's the syntax we wished for. What does that expand to? Well, the compiler would expand it to a map. And if we look at the map operation on generator, then that's what it comes down to. It would say, well, the function f, that's this closure here, and you see it here, gets applied to the generate method from the random number generator on the left-hand side of the map, the receiver of the map. And that, of course, can be simplified by just doing a so-called beta reduction. So we apply the function to the argument and we reduce it in one step to what you see here. So that's exactly the generator for booleans that we started with. Let's try the same thing with pairs. So here's already the expanded syntax of the for expression for pairs. If we expand the map, then that's what we get here. If we expand the flat map, we get this expression here. So let's look at this in a bit more detail. We get a generator for pairs from of t and u. Its generator method gives you the generator here that does the generation of the pairs like that. And then we call generate again on this nested generator. If we simplify that expression, then we get again the expression we started with, a pair where we generate on the t and the generator value on the u generator and collect the two in a pair. Let's have a look at some other building blocks for generators. A useful, even though very simple building block is the single generator. That is in a sense a borderline case in that it always gives you back the same random value t. So the value is not that random after all. So you get the value that you want to return, and generate each time returns that value. Another building block is the choose generator. That would give you an integer in the interval between low and high. The way it would do that, it would take an arbitrary random value from the integers and would normalize it to be in the interval between low and high using this modulo expression here. The last generator, one-off, can pick an arbitrary value from a list of choices. So you can call it, for instance, like this. One-off of three colors, red, blue, yellow, would give you a random color that can be red, blue, or yellow. One-off takes a vararg argument t star, which means that you can give it as many choices as you want. And what it would do then is it would choose an integer between 0 and the number of choices that you have passed, and you pick the choice which is at this index in the list of choices that are passed by T star. So with these building blocks we can now set out to write random value generators for some more structured types. Let's start with lists. How would you generate a random list? Well, one way to do it is first to flip a coin where the list should be empty or non-empty. That's done with this generator here. We go through the booleans, we record the result in is empty. Then if the coin gave us that the list should be empty, we always return the empty list. Otherwise we return a non-empty list. So how would we return always the empty list? Well, that's just the generator single that always returns a nil. How would we get a generator that generates a non-empty list? Well, that's another for, where we say now for getting a non-empty list of integers, we have to pick a random integer here in the head left arrow integers generator, and then we have to follow that with a random list. So we have here a call, a recursive call to the list generator. The random value that comes out of that is called tail, and all that is left is that we need to compose the head random integer with the tail random list. So here's an exercise for you. Can you implement a generator that creates random tree objects? Such objects would be of type tree, and the tree trait would have two case classes, two cases. A tree could either be an inner node consisting of two subtrees, or it could be a leaf consisting of an integer. So let's open a worksheet to see how we would do this. I've opened the worksheet generators, which contains some basic generators that we need, the integers and the booleans. What we would do now is go bottom up. So how to do a generator for leaves? Well, that one is simple. We just say, well, we need a random number, and for each random number that we get, we produce a leaf with that random number. So that covered leaves. How about inner nodes? Here's a generator for an inner node. What we do is we generate a random tree, call it L, generate a random tree, call it R, and produce a new inner node, call it L, inner of L and R. Now finally the trees generator is, you see here. So as in the case of list, we flip a coin whether we want a leaf or an inner node. That's done here. If we want a leaf, then we turn to the leaves generator to produce a random value. Otherwise, we return to the inners generator. Let's see how this would work in action. So we take the trees generator and generate a random value. So what did we get here? Well, we got a tree that consists of two leaves in an inner node, and then they themselves are the left tree of another inner node with a leaf on the right. That's just one possible random tree. The next time I run this operation, then of course I would get a different node. So this time the tree I got was much smaller. Let's try a third time. Now it was much bigger. So you see what you get is real random values in the tree domain. An important application of random value generators is random testing. So you know about tests, in particular unit tests. There the idea is you come up with inputs to a program function or a set of program functions, and then you have an assertion or a post condition that should hold when these functions are run on the input. So the post condition is a property of the expected result. And then you run the tests to verify that the program satisfies the post condition. But the point is, after all the tests pass, hopefully, then you only know that the program satisfies the post conditions on these test inputs. There might be others where the program still could fail. So typically you would need to be smart about finding a lot of good test inputs that exercise the program in all possible program paths. So a question is, can we do it without all the hassle of finding these test inputs? Can we do completely without the test inputs? And the answer is yes, in some cases at least, if we can simply generate random test inputs. So all the hard work of coming up with the input values we leave to the random value generator. So here's an example how we can do that with the generators that we have defined so far. Here's a test function It takes a generator that gives us input values in some domain t, and it takes the number of times we want to run the test on different randomly generated values. And then it takes a test function that returns true or false. So the idea is it returns true if the test passes and false when it fails. And what it would do then is we would, for I from 0 to number of times, generate a random value and then assert that the test function returns true, and if not, we will give you this assertion error. If everything goes well, then it would print that we have passed the number of times test. So here's a use case of this test function. So we would apply it to the generator that gives us pairs of lists. And then the function would say, well, given two random lists xs, ys, two arbitrary lists xs and ys, is the length of their concatenation always longer than the length of the list xs itself? Question to you, does that property always hold? Well, one way to answer this question is to simply try it out. We have all the random number generators. We have the test function. I have assembled them in another worksheet where you see all the generators here. And finally, we have the test function that you see here at the end. Let me just run this test on pairs of lists. And the function would be that given two arbitrary lists xs and ys, we want to postulate that the length of the concatenation is greater than the length of just xs. And what do we get? Well, we get a counterexample, an assertion error, which says the test failed for, and here you have the counterexample. The first is a list consisting of a single element. You see that's a random value that we have in here. The second list is empty, and in that case, of course, the length of these two lists is 1, and whereas the length of xs is also 1, so the two lengths are equal, and the assertion fails. So the answer to this question here is obviously the property does not always hold, which have just found a counterexample. Now, the idea of these random tests and random value generators is embodied in a very useful tool that you can use for your Scala programs. The tool is called Scala Check, and it is modeled to a large degree after a tool called Quick Check, which exists for Haskell programs, and variants of Quick Check have been developed for quite a few other languages. Erlang is one example, and in the form of Scala Check, also for Scala. So the idea is, just as you've seen, Quick Check would come up with random value generators. It's a bit smarter than what you have seen in that it can actually generate sometimes the random values if you just give it a type. So it knows how to generate random values for types that have a certain form. And then you would run tests similarly to what you've seen with the test function. Only in Scala Check it's called for all. So you would just write for all, and then you would have the predicate that says, well, on which domains you want to run your test, in this case two lists of ints, and what property should hold. So that's the property that you want to test here. And the test would, similarly to what you've seen, run a prescribed number of times, which you can configure. Scala Check is quite a bit smarter than what we've seen also, in the sense that if a test fails, it can minimize the counterexample. The counterexample you saw was a list with a rather large random number. That was the first one it found that falsified the test. Whereas what Quick Check and Scala Check would do in this case is they would then try repeatedly to find smaller and smaller examples until the example is something that is essentially a local optimum. It would typically, such a smaller example would be easier to understand as a counterexample than just an arbitrary random value. If you want to find out more about Scala Check, then there's a tutorial on the course page, and Scala Check will also be used in the first assignment that you're going to do in this course.